Students, Happy New Year to all. Today we start the next topic of this chapter oscillation, that is energy in SHM. Energy means we find out the total energy, and we know that the total energy means kinetic energy and potential energy together. So let's start today's topic, total energy in SHM. The SHM in a simple harmonic oscillator, it is a sum of kinetic energy and potential energy. Or you can say that it is a partly kinetic energy and partly potential energy. In simple harmonic oscillator, when the body or the object is displaced from its mean position or equilibrium position by doing work on it, potential energy, that energy is called potential energy, or the body acquires potential energy. Okay, and when the body is released, it begins to move back with a velocity that is called kinetic energy. That means we know that kinetic energy, the energy possessed by virtue of its motion. When the object is in motion, that is called kinetic energy, and when the object is at rest, that energy is called potential energy. Clear? So we before we find out the total energy, first of all we find out the expression of kinetic energy and the potential energy. Then we adding this to kinetic energy and potential energy, so we can easily get the total energy. Clear? Okay, so let's first start with the kinetic energy. Kinetic energy, the of a SHM. So in SHM, we know that we considered one equation, differential equation, in terms of cosine or sine. Here I will consider as a cosine function. So the displacement of the particle or the object which execute SHM, that is x equals to a cos omega t plus phi naught. A is the amplitude, phi naught is a initial phase. So because kinetic energy, we know that kinetic energy means half mv square. We need velocity. So displacement is given. So if we differentiate it with respect to time, we get the velocity. So v equals to dx by dt. So if we differentiate this equation, we get minus omega a sine omega t plus phi naught, because when we differentiate cos, it will be minus sine. Now the half mv square, in place of v square you put this value, so we get half m omega square a square sine square omega t plus phi naught. Now this a square sine square omega t plus phi naught, this term we can written like this way in terms of cos. So why we write in terms of cos? Because we uh, get the expression in terms of displacement, in terms of x. So here you see that we can write sine square. We know that sine square plus cos square equals to 1. So sine square means 1 minus cos square. So in place of sine square, we can write 1 minus cos square omega t plus phi naught. So if we multiply a square, so one term we get a square cos square omega t plus phi, and a cos omega t plus phi naught, that is a x. So in place of this, we can write x square. So we get the kinetic energy, that is equals to half m omega square into a square minus x square. Okay, now m omega square, that is equals to k. When we find out or derive the formula for differential equation in SHM, this term we derive this term k, omega square equals to k by m. If you forgot, just once you see that differential derivation of differential equation in SHM, you can get this expression, omega square equals to k by m. So in place of omega square, if we put k by m, so m cancel, we have half k a square minus x square. So kinetic energy equals to, we get half k into a square minus x square. This is the kinetic energy. Now we derive potential energy. Potential energy, that means when the displacement of the object from its equilibrium position, we know that a force is acting on it which is try to return back to its initial position. That force is called restoring force, and that restoring force expression we know that F equals to minus k into x. Why we use the minus sign? Because the displacement and the restoring force direction are opposite in to each other. And when it will, if we consider when the object is displaced a very small distance dx, so the work done against this restoring force, it will be also be very small. So that is dw equals to minus f into dx. If we put the value over there, you get plus kx into x, dx, because f equals to minus kx, minus minus plus, so kx into dx. So this is for the small distance dx or small displacement. Now, if we want to find out the total work done in a moving particle from its mean position means rest, x equals to no displacement, x equals to 0 to its displacement. The displacement here we consider the distance at a distance x. So, to 0 to x. So, we integrate both sides. So, w equals to integration dw integration 0 to x kx into dx. So, if after integration we get w equals to half k x square. And we know that this work done is stored as a potential energy, and not because here we find out the potential energy, that's why, but we know that the work and energy are um, equal to each other. Okay, so in place of kinetic energy, if we find out the kinetic energy, if any situation is there, then we find out the work done first, then we can say that that work done is stored as a kinetic energy inside the body. So because here we find out the potential energy, so any work done, any kind of work done is stored as a energy. Either it will be kinetic or the potential. So potential energy equals to half k x square. Now in place of k, if we can write m omega square, so m omega square x square and x equation we consider. So we have two equation of potential energy, one half k x square in terms of displacement, another one in terms of cosine function half m omega square a square cos square omega t plus phi naught. Clear? So now we easily find out the total energy, sum of kinetic energy plus potential energy. So here we use kinetic energy and potential energy, same equation. If you write the equation in terms of cos, so for both cases you can write the cos. Okay, if you write the x function in terms of x, so both side you can write, for both cases kinetic energy and potential energy you can write x. So here kinetic energy half k a square minus x square plus potential energy half k x square. So both are in terms of k and x. Now after solving this one, we get total energy equals to half k a square. In place of k, you can write m omega square. So total energy equals to half m omega square into a square. Okay, this is one equation for total energy. Another one equation you can write, and that is omega equals to, because omega equals to 2 pi into nu. So in place of omega, if you put it over there, so you get the total energy in terms of m or nu and amplitude a. So 2 pi square m nu square a square. Okay, so we can say that the total mechanical energy of a harmonic oscillator is independent of time or displacement. So we can say that in the absence of any frictional force, the total energy of a harmonic oscillator is conserved. Okay, so from this it is clear that the total energy of a particle in SHM, it is directly proportional to the mass of the particle, mass of the particle, directly proportional to the square of its frequency nu and mu, and sorry, nu not mu, and directly proportional to the square of its amplitude a. All are directly proportional to each other. Okay, Now, graphical representation of this, how can we represent the kinetic energy, potential energy, and total energy in graphical method or in graph? So first of all, if we need any kind of graph, we need some data to some points x and y values we need. Okay. So first of all, we find out at mean position and at equilibrium position, because these two positions are fixed in case of a SHM. Mean position means no displacement, and extreme position means x equals to plus minus a. So in mean position x equals to 0, kinetic energy will be half k square, but potential energy will be 0. Now at so we can say that the mean position all energy is kinetic energy, and the extreme position x equals to plus minus a. Plus means positive x side, minus means negative x side. So total kinetic energy will be 0, but the potential energy is half k square. So at extreme position on both sides, the all energies are the potential. Kinetic energy is 0. So in mean position, kinetic energy, all energy is the kinetic energy, potential energy is 0. And in extreme position, kinetic energy is 0, all energy will be potential energy, that is half k a square. Now, if we plot this in figure, we get this kind of figure. This figure shows that the vibrations of kinetic energy K, potential energy U, and the total energy E with the displacement X. The graphs for K means the kinetic energy, and the U, that is the potential energy, are parabolic, while the for E, that means total kinetic and total energy, is a straight line parallel to the displacement axis. Displacement axis we plot as x. So the E is the total energy that will be the parallel to the x axis. But the kinetic energy and the potential energy are parabolic. Kinetic energy and the potential energy will be parabolic. Okay. So at x equals to 0, the energy is all kinetic, and at x equals to plus minus a, all energy are potential energy. Clear? Okay, there is some numericals. Easily you can, I think you can understand. Just directly use the formula for kinetic energy, potential energy, total energy. Once you just go through it, three examples are there. Okay. If you did not understand anyone, three examples are there. Anyone, if you did not understand, please let me know. I will discuss it. I think there's a no problem. Directly use the formula, nothing else. Clear? Okay. So if you have any problem, please write in a comment box. Thank you very much. Have a nice day.